Alright, so now we will start with the solution. This is actually the second problem, and you can see this is just the same problem. We solved our first problem, and this question it is same, all the values, everything same. The heat exchanger type it is also same, but why we select the same problem? Because I actually want to show you the difference between two different methods, the log mean temperature difference method and the effectiveness and NTU method. So we are going to solve this question by using the effectiveness and the NTU method. So let's start with the solution. I'm not reading the question because if you already solved the first question, then you already know it. So we need to calculate the length of the pipe of the heat exchanger to achieve the desired heating. So that's our ultimate target. We will calculate the length. So everything same, all parameters same. So we'll only calculate the length by using different method instead of log mean temperature difference method. So here you can see the values. So if we start with the flowchart, that what we usually do, that we need the length. So we don't know length, it is from the surface area. We are not going to use the log mean temperature difference method, so that means this method is different. But what we know from the theories that the NTU it is called number of transfer unit. This is kind of function of the heat transfer surface area. NTU, it is actually UAS and C mean. This AS, it is actually the heat transfer surface area. So if we calculate the NTU by using the NTU and the effectiveness, the NTU approach, then we will get the surface area. That means we need the NTU value. And in this case, we are solving the problem. You see, the cold fluid is going this way, hot fluid is coming from the other way. So it is a counter flow heat exchanger. So we will get the NTU expression for counter flow heat exchanger. It is 1 over C on ln epsilon over 1 minus C epsilon minus 1. I will show you for counter flow heat exchanger. Okay, just a second. You see, for counter flow heat exchanger, it is actually the relations for NTU. You see the first one for concentric tube that we are solving. For parallel and counterflow, we are solving counterflow. So look, for counterflow, we got two expression, one for the CR, which is less than 1, which is CR equal to 1. Okay, I will discuss later on. So this is actually, we need the NTU value, okay, the NTU expression. And to get the NTU, you saw there, we actually need the value effectiveness E, and effectiveness is eventually Q over Q max, the formula. So you need to calculate the rate of heat transfer, okay, and the max possible heat transfer as well. So what we will do, we will calculate the Q, we will calculate the Q max, the max possible heat transfer, and we will calculate the C, that means the C main and the C max ratio, this value. So this will be the overall flow chart if we want to solve this problem. Look, we are not going to use any log mean temperature difference here. So this is the overall flow chart we are going to follow for this problem. So to save some of our time, I'm not writing the assumptions and the properties here, anything, because you already know we solved the first problem. So we will just start with the analysis. Okay, we will start with the analysis. So at first we will calculate the heat capacity rate for the hot and the cold fluid, the heat capacity is, because in the effectiveness and NTU method, it should be our first task, and we need to check whether which capacity rates are minimum. I discussed, because when we will calculate the max possible heat transfer rate, we need to use that formula. For max, let's say it is max possible heat transfer rate, so it is, the formula is C mean, okay, into delta T, and C mean is, you know the formula, C mean, that means it is the minimum value of Cc or Cis. So we C mean, it is actually the ratio, it is the minimum value between the wet fluid capacity rate or cold fluid capacity rate. So if we start with the analysis, guys, the first thing we need to do is we need to calculate the Cc and Cis. So we discussed everything during the lecture. What is Cc, what is Cis? So the formula for Cc, cold fluid, it is the mass flow rate for the cold fluid and the specific heat of the cold fluid. Okay. So I told you that I'm not going to write all the properties here again because we did it last time. So we know the cold fluid mass flow rate, it is 1.2, and the water specific it is 4.18. So we'll get it is 5.02 kilowatt per Kelvin. And the hot fluid specific heat, it is the mass flow rate for hot fluid and the specific heat for hot fluid. So the mass flow rate is 2 and Cp equal 4.31. So it will be 8.62 kilowatt per Kelvin. Okay. So this is Cc and this is Cis. Okay. So we got these two value. And from these two value, what we can write down, guys, C mean, that means the minimum capacity value in between this C mean, or we can say it is Cc. It is actually, yes, C mean is the cold fluid capacity rates, 5.02. So we can say it is 5.02 kilowatt per Kelvin. We need this one when we will calculate the the max possible heat transfer rate. So this is C mean. And from the effectiveness and the NTU formula, we know there is other value C. It is the capacity ratio, the heat capacity ratio. Heat capacity ratio C, it is actually the ratio of C mean and C max. So then C mean equal, it is 5.02, 8.62. So C equal 0.582. So C equal 0.582. This is the the C capacity ratio we got. Depending on this C, so here we calculated this C, and we calculated the capacity ratio as well. Look, guys, depending on this value, we will select our expression for the NTU. So it is important. We have two expression for NTU if the C value is greater than 1, or less than 1, or if it is equal to 1. Okay, so we'll discuss that on when we'll solve the NTU relations. Once we have this C, then let's calculate the Qmax. Qmax is the max possible heat transfer. So the max possible heat transfer we can define by using Qmax, and the formula is C mean and the temperature difference. Definitely it is T hot fluid inlet and the cold fluid inlet. So here, see what I write down, C mean, and this is the temperature difference, the hot fluid inlet and the cold fluid inlet. Here, some of you may ask me, okay, this is actually the hot fluid inlet, okay, and this is the cold fluid inlet. Why you are taking, so when you did the log mean temperature difference, then we said, okay, this 2 is delta T1 and it is delta T2, right? That we did. Now I'm suddenly telling, okay, the temperature difference here, this delta T, this value, it is the hot fluid inlet and the cold fluid inlet. Why not like the difference between this and this, or this? Actually, max possible means the temperature difference will be maximum. Okay, the temperature difference will be maximum, and we found this is not actual heat transfer rate. It is what is the maximum possibility. So we found the temperature difference at the hot fluid inlet and the cold fluid inlet is the highest, so we will use that one. This temperature difference, when you will calculate the max possible heat transfer rate, you need to think about it. So C mean, it is 5.02, and this is 160 minus this 20. So we will get the Q max is 7028 kilowatt. Okay, so this is the max possible heat transfer rate. But what is the actual heat transfer rate? Actual heat transfer, because we actually need the actual heat transfer rate as well, because the effectiveness is the actual heat transfer minus the max possible heat transfer. So calculate the actual heat transfer rate. Q, we say it is M, Cp and delta T. So this is here water will gain the temperature, so we will use like what we did for previous problem, the outlet temperature and the inlet temperature. Here, look here, this is the water is going through this, so the outlet temperature is 80, inlet temperature is 20, so we'll take that one. Mass flow, it is 1.2, specific heat 4.18, and it is 80 minus 20, so this is 301 kilowatt. We did the same calculation for the first problem. So now once you have these two, Q max and Q, then calculate the effectiveness from here. Once we have this effectiveness, we will go for NTU. All right. So the effectiveness, we'll say psilon equal Q over Q max. Q is 301, Q max is 702.8, so it will be 0.428. That's the effectiveness value. Once we got this effectiveness value, then we can use this table here. We can use this table from here. See the second one, equation 1.29b. For counterflow, we have the counterflow problem, and we got two relation for NTU. The first one is for the CR, capacity ratio less than 1. So in our problem, we got the CR is less than 1. So we are going to use this one. Okay, 1 over C minus 1 ln, this expression. So I'll write it down here. So the NTU, the number of transfer unit relation, it will be 1 minus C1 or CR1, whatever it is epsilon minus 1 and epsilon C minus 1. So we know C equals 0.582. I think we calculated here. Yes, you look here. So now minus 1, this is ln, epsilon is 0.428, we just calculated, yes, minus 1, and it is 0.428 into C, 0.582 minus 1. So we will get this NTU is 0.651. Once we have this NTU, we know the relations of the NTU. It is equal UAS over C mean. So that means the surface area, it will be NTU C mean over the overall heat transfer coefficient. So NTU is 0.651. C mean is C mean, I forgot the value for C mean. It is 5.02 kilowatt per Kelvin. Okay, so we can write it is 5.02. That means 5020. Okay, watt per Kelvin. And the the heat transfer coefficient is 640 watt per meter square Kelvin. So it will be the surface area 5.1 on meter square. So this is the heat transfer surface area. And now you know heat transfer surface area, aka is equal pi dl. So L is AS over pi d. So AS equal 5.1 on, pi is 3.1416, and the diameter is 0.015. It was in centimeter, I guess, yes. So the length we got 108 meter. Previously when we solved the other problem, by this problem by using the log mean temperature difference, I can remember maybe it was 109, and in this case you see we got 108. So that's very close. So that's actually what we did, and I believe that your heat exchanger report, when you will prepare your heat exchanger report, you need to use some similar formula to calculate the surface area or the heat